Section 250.24. A5 of the National Electrical Code addresses the grounding of service equipment, stating that the grounding electrode conductor shall be connected to the grounding bus in the service equipment enclosure. Using the neutral bus as a grounding bus is not a safe or code-compliant practice for several reasons. Firstly, electrical isolation. The neutral and grounding conductors are not allowed to be connected together except at the service entrance. If they are connected in the panel board, they could create a parallel path for fault currents, increasing the risk of shock and fire. Secondly, overloading. The neutral bus is designed to carry current on one leg of the circuit. Connecting the equipment grounding conductor and ground wires to it would overload the bus and create a potential fire hazard. Thirdly, confusion. Identifying the equipment grounding conductor and ground wires when they are connected to the neutral bus can be challenging, increasing the risk of miswiring and electrical accidents. The correct way to ground a 240/120 service entrance panel board is to install a grounding bus and connect the grounding electrode conductor, equipment grounding conductors, and outgoing ground wires to it. The grounding bus must then be bonded to the neutral bus through the grounding bonding pin. Connecting the equipment grounding conductor and outgoing ground wires to the neutral bus is not a safe or code-compliant practice. It is essential to install a separate grounding bus and follow the proper grounding procedures to ensure the safety and reliability of the electrical system. The purpose of grounding in electrical systems is multifaceted, primarily focusing on safety and providing a low-impedance path for fault currents. Grounding ensures that metallic enclosures of electrical equipment, such as panel boards, are at or near ground potential. This minimizes the risk of electric shock to individuals who might come into contact with these enclosures. When a fault occurs, such as a short circuit from a live conductor to the enclosure, the grounding system provides a low resistance path for the fault current to flow back to the source. This high current flow causes the overcurrent protective devices, like circuit breakers or fuses, to trip quickly, disconnecting the faulted circuit and preventing prolonged exposure to dangerous voltages. The equipment grounding conductor, or EG, plays a vital role in this process. It is a dedicated conductor that runs alongside the circuit conductors and connects the metallic enclosures of electrical equipment back to the grounding bus in the service equipment. In a properly grounded system, the EGC provides a direct path for fault currents, ensuring that the overcurrent protective devices operate promptly. The grounding electrode conductor, or GEC, connects the grounding bus in the service equipment to a grounding electrode, such as a ground rod, ground plate, or the metal water pipe system of the building. The grounding electrode provides a connection to the earth, which helps to stabilize the voltage of the electrical system with respect to ground. It also provides an additional path for fault currents to flow back to the source. Bonding refers to the process of connecting all metallic parts of the electrical system together to create a continuous electrical path. This includes bonding the equipment grounding conductors, metallic conduits, enclosures, and other metal parts. Bonding ensures that all these parts are at the same potential, minimizing the risk of voltage differences and electric shock hazards. The neutral conductor is a current-carrying conductor that provides a return path for current in a single-phase or three-phase electrical system. In a 240/120 volt single-phase system, the neutral conductor is typically connected to the center tap of the transformer secondary, providing a voltage of 120 volts between each hot conductor and the neutral. The neutral conductor is normally grounded at the service entrance, creating a reference point for the electrical system. It's important to distinguish between the neutral conductor and the equipment grounding conductor. The neutral conductor carries current under normal operating conditions, while the equipment grounding conductor only carries current during a fault. Connecting the equipment grounding conductor to the neutral bus, except at the service entrance, can create a hazardous situation. This is because the equipment grounding conductor would then carry current under normal operating conditions, potentially overloading the conductor and creating a shock hazard. Furthermore, connecting the equipment grounding conductor to the neutral bus can compromise the effectiveness of the grounding system. If a fault occurs, the fault current would have to flow through the neutral conductor before reaching the grounding electrode. This can increase the impedance of the fault current path, slowing down the response of the overcurrent protective devices and increasing the risk of electric shock and fire. The National Electrical Code, or NEC, provides specific requirements for grounding and bonding electrical systems. These requirements are designed to ensure the safety and reliability of electrical installations. Section 250 of the NEC covers grounding and bonding, and it provides detailed guidance on how to properly ground and bond electrical systems. Some key NEC requirements for grounding and bonding include: firstly, the grounding electrode conductor must be connected to the grounding bus in the service equipment enclosure. Secondly, the equipment grounding conductors must be connected to the grounding bus in the service equipment enclosure. Thirdly, the grounding bus must be bonded to the neutral bus at the service entrance. Fourthly, all metallic parts of the electrical system must be bonded together to create a continuous electrical path. When installing a 240/120 service entrance panel board, it is crucial to follow these NEC requirements to ensure that the electrical system is properly grounded and bonded. Failure to do so can create a dangerous situation and increase the risk of electric shock and fire. If the panel board does not come with a grounding bus, it is necessary to install one. The grounding bus should be securely mounted inside the panel board enclosure and connected to the enclosure with a bonding jumper. The grounding electrode conductor, equipment grounding conductors, and outgoing ground wires should then be connected to the grounding bus. The grounding bus should also be bonded to the neutral bus at the service entrance. This can be done by installing a bonding jumper between the grounding bus and the neutral bus. The bonding jumper should be sized according to the NEC requirements. When connecting the equipment grounding conductors and outgoing ground wires to the grounding bus, it is important to use the correct size and type of connectors. The connectors should be listed for grounding purposes and should be properly tightened to ensure a good electrical connection. It is also important to label the equipment grounding conductors and outgoing ground wires so that they can be easily identified. This will help to prevent miswiring and ensure that the grounding system is properly maintained. In summary, proper grounding and bonding are essential for the safety and reliability of electrical systems. When installing a 240/120 service entrance panel board, it is crucial to follow the NEC requirements for grounding and bonding. This includes installing a grounding bus, connecting the grounding electrode conductor, equipment grounding conductors, and outgoing ground wires to the grounding bus, and bonding the grounding bus to the neutral bus at the service entrance. By following these procedures, you can ensure that the electrical system is properly grounded and bonded, minimizing the risk of electric shock and fire. The installation of a grounding bus in a service panel, especially when one is not originally included, requires careful consideration of several factors, primarily focusing on safety, code compliance, and the long-term reliability of the electrical system. A grounding bus, also known as a ground bar, serves as the central connection point for all grounding conductors within the panel. These conductors include the grounding electrode conductor, which connects the panel to the grounding electrode system such as ground rods or a metallic water pipe, and the equipment grounding conductors, which provide a ground path for metallic enclosures of electrical equipment and appliances. The primary function of the grounding bus is to provide a low impedance path for fault currents, enabling overcurrent protection devices such as circuit breakers or fuses to quickly trip and disconnect the circuit in the event of a ground fault. This rapid disconnection minimizes the duration of exposure to hazardous voltage levels, thereby protecting individuals from electric shock and preventing potential damage to equipment. When adding a grounding bus to a panel that did not originally include one, it is crucial to select a grounding bus that is appropriately sized for the panel's ampacity and the number of circuits it serves. The grounding bus must have sufficient capacity to accommodate all of the grounding conductors that will be connected to it, and it must be made of a conductive material, such as copper or aluminum, that is compatible with the grounding conductors. Installation of the grounding bus must comply with all applicable requirements of the National Electrical Code, specifically Article 250, which covers grounding and bonding. The grounding bus must be securely mounted to the panel enclosure, and it must be electrically bonded to the enclosure to ensure a continuous ground path. Bonding is the process of connecting all metallic parts of the electrical system together to create a low impedance path for fault currents. This includes bonding the grounding bus to the panel enclosure, as well as bonding all metallic conduits, enclosures, and equipment to the grounding system. The NEC requires that all bonding connections be made using approved methods and materials, such as bonding jumpers, bonding screws, or exothermic welding. In addition to the grounding bus, the grounding electrode conductor, or GEC, plays a critical role in the grounding system. The GEC connects the grounding bus to the grounding electrode system, providing a path for fault currents to flow back to the source. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The grounding electrode system can consist of one or more grounding electrodes, such as ground rods, ground plates, or a metallic water pipe. The NEC requires that the grounding electrode system have a resistance to ground of 25 ohms or less. If the resistance to ground exceeds 25 ohms, an additional grounding electrode must be installed. The equipment grounding conductors, or EGs, are another essential component of the grounding system. The EGC provide a ground path for metallic enclosures of electrical equipment and appliances. The size of the EGC is determined by the size of the overcurrent protection device protecting the circuit, as specified in NEC Table 250.122. The EGC must be installed in the same raceway or cable as the circuit conductors. When installing the EGC, it is important to ensure that they are properly connected to the metallic enclosures of the equipment and appliances. This can be done using grounding screws, grounding clips, or other approved methods. It is also important to ensure that the EGC are continuous throughout the circuit with no breaks or interruptions. The neutral conductor is a current-carrying conductor that provides a return path for current in a single-phase or three-phase electrical system. In a 240/120 volt single-phase system, the neutral conductor is typically connected to the center tap of the transformer secondary, providing a voltage of 120 volts between each hot conductor and the neutral. The neutral conductor is normally grounded at the service entrance, creating a reference point for the electrical system. However, it is important to note that the neutral conductor should only be grounded at the service entrance. Grounding the neutral conductor at any other point in the system can create a hazardous situation. This is because the neutral conductor carries current under normal operating conditions, and grounding it at multiple points can create a parallel path for current to flow. This parallel path can cause the neutral conductor to become overloaded, leading to overheating and potential fire hazards. Furthermore, grounding the neutral conductor at multiple points can interfere with the operation of ground fault circuit interrupters, or GFCIs. GFCIs are designed to detect small imbalances in current between the hot and neutral conductors, which can indicate a ground fault. If the neutral conductor is grounded at multiple points, the GFCI may not be able to detect these imbalances, rendering it ineffective. Therefore, it is crucial to ensure that the neutral conductor is only grounded at the service entrance. This can be accomplished by isolating the neutral conductor from all metallic enclosures and equipment except at the service entrance. The NEC provides specific requirements for isolating the neutral conductor, which must be followed carefully. In summary, adding a grounding bus to a service panel that did not originally include one requires careful consideration of several factors, including safety, code compliance, and the long-term reliability of the electrical system. The grounding bus must be appropriately sized for the panel's capacity and the number of circuits it serves, and it must be installed in accordance with all applicable requirements of the National Electrical Code. The grounding electrode conductor and equipment grounding conductors must be properly sized and connected to the grounding bus, and the neutral conductor must be isolated from all metallic enclosures and equipment except at the service entrance. By following these procedures, you can ensure that the electrical system is properly grounded and bonded, minimizing the risk of electric shock and fire. Furthermore, properly labeled conductors and a clear understanding of the grounding and bonding system are crucial for future maintenance and troubleshooting. The NEC provides guidelines for identifying grounding and grounded conductors, and these should be adhered to strictly. Regular inspections of the grounding system are also recommended to ensure that all connections are tight and that there are no signs of corrosion or damage. Any issues identified during these inspections should be addressed promptly to maintain the integrity of the grounding system. When working with electrical systems, it is always important to prioritize safety. This includes wearing appropriate personal protective equipment such as safety glasses and insulated gloves, and following lockout/tightout procedures to de-energize circuits before working on them. It is also important to be aware of the potential hazards associated with electricity, such as electric shock and arc flash, and to take steps to mitigate these hazards. Only qualified and experienced electricians should perform electrical work, and they should always follow the NEC and other applicable codes and standards. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work for you. In addition to the technical aspects of grounding and bonding, it is also important to consider the legal and regulatory requirements. Many jurisdictions have adopted the NEC as law, and compliance with the NEC is mandatory. Failure to comply with the NEC can result in fines, penalties, and even criminal charges. Therefore, it is essential to be familiar with the NEC requirements and to ensure that all electrical work is performed in accordance with these requirements. Furthermore, it is important to obtain all necessary permits and inspections before starting any electrical work. This will help to ensure that the work is performed safely and in compliance with all applicable codes and standards. In conclusion, grounding and bonding are essential aspects of electrical safety. Proper grounding and bonding practices protect individuals from electric shock, prevent damage to equipment, and ensure the reliable operation of electrical systems. When working with electrical systems, it is crucial to follow all applicable codes and standards, prioritize safety, and only perform work that you are qualified to do. By following these guidelines, you can help to ensure that electrical systems are safe and reliable. The 400 amp service mentioned implies certain considerations for conductor sizing, overcurrent protection, and grounding electrode conductor selection. A 400 amp service requires conductors with sufficient ampacity to carry the load, typically calculated based on the connected load and demand factors. The National Electrical Code provides tables for determining the appropriate conductor size based on the ampacity and insulation type. Overcurrent protection for the 400 amp service is typically provided by a main circuit breaker or fuses rated at 400 amps. The overcurrent protection device must be properly sized to protect the service entrance conductors from overloads and short circuits. The grounding electrode conductor connects the service equipment to the grounding electrode system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. For a 400 amp service, the grounding electrode conductor typically needs to be a certain size copper or aluminum conductor, depending on the type of grounding electrode system used. The grounding electrode system can consist of one or more grounding electrodes, such as ground rods, ground plates, or a metallic water pipe. The NEC requires that the grounding electrode system have a resistance to ground of 25 ohms or less. If the resistance to ground exceeds 25 ohms, an additional grounding electrode must be installed. The 5 mains that feed the 5 distribution panel boards require proper coordination of overcurrent protection to ensure selective tripping. Selective tripping means that only the overcurrent device closest to the fault should trip, minimizing the disruption to the rest of the electrical system. This requires careful selection of the overcurrent devices based on their interrupting rating, time current characteristics, and coordination studies. The neutral bus in the service panel serves as the connection point for the neutral conductors from the branch circuits. The neutral bus must be properly sized to carry the neutral load, which is typically calculated based on the imbalanced load in the system. The NEC provides guidelines for calculating the neutral load and determining the appropriate size of the neutral bus. The bonding jumper between the neutral bus and the grounding bus is typically a copper conductor or strap. The size of the bonding jumper is determined by the size of the service entrance conductors, as specified in NEC Table 250.102. The bonding jumper must be securely connected to both the neutral bus and the grounding bus to ensure a low impedance path for fault currents. The little bolt-on ground bonding pin is used to bond the neutral bus to the panel enclosure. This bonding connection ensures that the panel enclosure is at the same potential as the neutral conductor, minimizing the risk of electric shock. The bolt-on ground bonding pin must be securely fastened to both the neutral bus and the panel enclosure to ensure a good electrical connection.